Welcome back to Chapter 10.2, Rest Mass and Relativistic Momentum. We're following the Grade 12 Queensland Physics syllabus and the textbook written by Walding, W-A-L-D-I-N-G. And as we saw last time, our images are from Back to the Future, the three movies. Fantastic movies, probably best movies ever made. And this time we've got Biff Tannen. We've got 1955 Biff over there. We've got 1985 Biff, this one here, which is the alternate reality to 1985. This is the real 1985 Biff, and that's him in the future. 2015 Biff, and that's Biff's son in 2015, looking cool. So that's the way we should have been dressing 2 years ago, as opposed to 1885 Biff, which is Mad Dog Tannen there. I hope you catch up with your Back to the Future. All right, Einstein asked this question. So if it takes more than a human lifetime to get to the stars, how could we possibly go there? If it takes, in our example in our last video that we did, we were talking about taking a trip to Rigel at something like 0.999 the speed of light. It's 800 light years away. So to us here on Earth, the trip would take 800 years. However, to those on board the spaceship traveling almost at the speed of light, the trip doesn't go 800 light years in distance, and it doesn't take 800 Earth years to do it. The trip itself is about 35.8 light years in distance and takes about 35.8 years to do the trip, give or take, because we're not quite traveling at the speed of light. So that's probably the answer to the question. You can do it if you can accelerate up to those speeds and hold it for that long. And there's the answer to that question there. How long did the trip to Rigel take? 35.8 years, and it was about 35.8 light years in length. So what are we looking at today? We're going to look at rest mass and relativistic momentum. We looked at time, as in proper time and relativistic time. We looked at length, proper length and relativistic length. But when it comes to mass, it's easy to think in terms of momentum, okay? Because the momentum, you may recall, P equals mv. It's a function of mass and velocity. And as this velocity is increasing, it's going to increase the relativistic momentum, and we'll see how that starts to affect its mass. We think in terms of momentum when Newton first looked at his equations such as force is mass times acceleration, his second law of motion. He actually came from it from a momentum point of view rather than simply F equals ma. We're going to come back to mass energy equivalence, Einstein's famous E equals mc squared equation, and look at how when we travel to these fast speeds, what starts to happen. So what are we going to do? We're going to calculate the momentum of fast moving objects, particularly its relativistic momentum. All right, we've got a nice, fantastic quote from the end of the first Back to the Future movie, where Marty McFly says, "You better back up, Doc. We haven't got enough room to get up to 88 miles per hour." And Doc says, "Roads? Where are we going? We don't need roads." You really should watch those movies. So, rest quantities. So, sort of define a few things again. We've looked at time and length in previous sections. So, when we say that t is greater than t naught, what are we talking about? The t naught means proper time. The t is relativistic time, as in that dilated time to the observer in a different reference frame. And likewise, the length is proper length at rest, as opposed to relativistic length from an observer in a different reference frame. And what we notice is, if this is considered to be the clock, where you only need one clock to time the start and finish of the event, as in the start point and finish point past that clock, you'll have a shorter time than if you need two clocks, a clock at the start and a stop clock at the end. Your relativistic time is always going to be longer than your proper time in, for example, this traveling spacecraft. But as far as length goes, your proper length is measured by the frame of reference that's not accelerating or not changing its velocity, like a spaceship would accelerate up to its speed and travel the 800 light years to Rigel, for example, it will be measuring relativistic length as opposed to here on Earth, which is proper length. So the inequality is different because we look at it from a different point of view. So, considering that, and there's the DeLorean taken off to go to the future, to go to 2015, which is obviously now the past. So what would m naught be? You would consider that to be the proper mass. Okay. Note our little points that we've got up the side here. M naught is kind of like your proper mass, or what we refer to as your Newtonian mass. Which brings us to this equation here. Similar equation. Note we've still got the Lorentz factor in there, but we're dealing with momentum. So momentum is a more useful calculation than straight mass. So PV is your relativistic momentum, and m naught is your rest mass, otherwise known as Newtonian mass, or proper mass, I suppose you could think if you use the same terminology we've been using before. So that's the mass at rest, and that's obviously a function of the velocity, as you can see on top of the equation there. Let's look at an example. So the Stanford Linear Accelerator can accelerate electrons to over 0.999 the speed of light. Calculate the Newtonian momentum and the relativistic momentum of the electron. So as far as Newtonian momentum goes, the one we saw back in Unit 2 when we were looking at linear motion. The relativistic momentum is the one we've just seen. That one there. Okay? And B, determine how many times greater the relativistic value is than the Newtonian value. Because what this is going to show us is that as our velocity increases, so our velocities are going to be increasing, as they go up, what it's going to do is increase our momentum. And that starts to become a problem the more and more you accelerate. So here's our solution. Part A, the Newtonian one, is this guy here. P equals mv. So what do we know? We know that the rest mass is that one, and that's in there. We know that we're traveling 0.99 the speed of light. So it's 0.99 times whatever the speed of light is, which gives us this one here. 2.73 by 10 to the negative 2 kilogram meters per second. Standard units, kilograms, meters, seconds. The relativistic momentum is our new equation we just saw, and it's the same deal. Plug the numbers in and see what comes out the other side. We don't need the 3 by 10 to the 8 because when we have it here, the c's will cancel out and we end up with the 0.999 squared. And what do we end up with? 6.11 by 10 to the negative 21 kilogram meters per second. So you can see that it's a few orders of magnitude different. It's not just from 2 to 6, but it's 10 to the negative 22 versus 10 to the negative 21. So part B is a useful calculation. What is the ratio? So we simply divide one by the other. And the 6.11 divided by the 2.73 is 22.4. That tells us that the relativistic momentum is 22.4 times greater than the momentum at rest, or the Newtonian momentum. So that electron has 22.4 times more momentum than what it did at rest. Okay, if it was just traveling in a Newtonian sort of fashion. It's telling us that the momentum is starting to build, which means it's harder and harder to move the mass the quicker and quicker we go. Let's look at another one. Calculate the speed of a 1 gram copper target traveling at a relativistic speed with a momentum of 500,000 kilogram meters per second squared. All right, so think, what was our formula? Pause the video and write it down now. Don't copy me, write it down. The Lorentz factor bit on the bottom there should be pretty straightforward to you because we've done it a few times now, and it's in every one of our equations. If you've got that, you should be able to plug the numbers in. It's telling you to calculate the speed. What is the speed in our equation? That's our velocities. What do we know? We know the speed of light. That's a number. We know the mass. It's 1 gram at the top there. And we know this momentum because it gave it to us there. You should be able to plug those numbers in and do it. And I encourage you to pause the video before you go on. See if you can get it yourself before you look at the solution. You'll learn a lot more. So there's our formula. Just chuck the numbers in like I just told you. Now, once you put the numbers in, it's just an algebra thing. So the 500,000 went in there. The mass, the mass was 1 gram, standard units. And then we start to plug all our numbers in and see what we can work out to find V, the velocity. Everything else is just the algebra from there on. For example, this Lorentz factor, we take over that side, and that's why it ended up there. We want to get rid of that square root, so we square both sides. So everything is squared, and that's why the square root sign disappears. In this line here, we've got a constant outside of a set of brackets, so 25 by 10 to the power of 10 times 1, and v squared over c squared times 25 by 10 to the power of 1. You're just expanding the brackets is all you're doing. All right. At the same time, we're isolating v squared on his own. How do I do that? This is a multiply here, so if we divide by that, we'll get rid of him. And that does all that for us. So that's that bit we'll put over the other side first. Then we did this expand brackets thing to get rid of this. And then we just keep going with our algebra. Keep rearranging it until you get what you need. Notice there's one point down here where we've got c squared. We substitute in the value for c squared, 3 by 10 to the 8 squared. Once we have that, it starts to simplify quite nicely. Down the bottom here, 2.78 v squared plus v squared. Think of your grade 7 algebra that you would have done. 2.78 apples plus another apple means you've got 3.78 apples. Divide by that number and you'll leave your v squared on his own. So the line that's missing there is 25 times 10 to the 16, equals 3.78 v squared. Divide both sides by the 3.78. That's what we've done. And we end up with that guy there, and you can find out v from that point there. So the velocity is 2.57 by 10 to the power of 8. Now it says there that that's 0.857 c. How do you work that out? Because it's 2.57 over 3 by 10 to the 8. So all I've left out is the times 10 to the 8 for both the top and bottom of that. And when you do that, it's 0.857. So you know it's 0.857 the speed of light. Before we go on, are we not just happy that this ridiculous double tie setup didn't actually catch on by 2015? I mean, let's face it. As cool as that looks because you're emulating Marty McFly, yeah, I don't think it'd actually be really that practical. All right, a couple of challenges there. I encourage you to pause, have a look at those. But I do point your attention to these little clouds I've got here. How many of you actually do these challenges? Ask yourself the question, why did the author include them in the textbook? Why do I include them here? And I suppose it comes down to, where do you want to end up by the end of this course? It's your learning and you need to be responsible for it. Do you want to tend towards the ATAR below 30 end of the scale or the ATAR above 90 end of the scale? Or which way do you want to head in your ATAR? Having a go at these is going to push your ATAR up higher because you'll understand the work a bit better. If we look at these questions, does an electronic balance measure rest mass or relativistic mass? What does it do? Is it moving? No. We tend to consider it to be at rest. Even though the Earth is in motion, we tend to consider the Earth as a nice inertial reference frame. So it is measuring your rest mass. If the scales were travelling at velocity, then we would consider it relativistic mass. And the next one here, speed. An unstable particle is at rest and suddenly decays into two fragments. One of the fragments has a speed of 0.6 c and a mass of that. The other has a mass here. Determine its speed. This takes us back to our previous work in Unit 2 and 3 on motion. Remember that your initial momentum equals your final momentum. Or written a different way, the sum of the momentum should be zero. Momenta should be zero. So the momentum of particle A plus the momentum of B should be equal to zero, because it's like when this thing explodes, one will go one direction and the other will go the other direction. And if this is a positive velocity, this will be a negative velocity, and hence they'll cancel each other out. So initial still equals final. That should be enough to get yourself started on this this particular question. In case you do have a crack at it and you do want to know what the answer is, the velocity of particle B is 0.184 c. Make sure you write those numbers properly. Don't get them wrong. I lost marks when I was at school because I wrote a zero wrong, and it's annoyed me ever since. Make sure it doesn't happen to you. Anyway, there's your answer. See if you can have a crack at it. You know what P is, mv, yeah, but that's the Newtonian one, but we're not really looking at that because we're talking about relativistic speeds. So use your other equation that we've dealt with, which is oops, 1 minus that one there. That will be what you put in for there and there. See if you can get to this answer. Right, mass energy equivalence. This sort of comes back to some of the stuff we've discussed before. Remember Einstein's famous equation? We did talk about this back in Unit 1. We talk in these terms. We don't really consider proper energy or anything like that because we're trying to distinguish from kinetic energy, which is the energy of motion. All right, it starts to get a bit weird when you look at those things. But I will point out, I do encourage you to check out this page of the textbook. Page 283 has got a great calculation that shows that if you charge your mobile phone for 2 hours, it will gain mass. Why is it gaining mass? Because you're adding energy into it. And remember, or more correctly, it's a change in energy. So what does that tell you? That tells you that if this one is increasing, that's a constant, that must increase as well because you are putting energy into your phone. How did we get to a billionth of a gram? Think about some of the equations we did back in Unit 2. Remember? Oh, that's a T. Work is voltage times current times time. If you know the voltage of your phone, you know the current that you're putting in, and you're charging for 2 hours, that will give you work. Work is measured in joules. Joules is energy. That is the E in the E equals mc squared part. So that number there becomes that. That's constant. Find out the unknown. How much is the mass? Because that is delta E. All right, this stuff here is basically some of the stuff we did way back in Unit 1 on binding energy of atoms back when we did our nuclear physics. We've got 10.2c and 10.2b. In C, we've got to calculate the binding energy in joules, and we've got a mass defect given to us. And in 10.2d, we've got a rest mass here, and its entire mass, it decayed, and its entire mass was transformed completely into energy or electromagnetic radiation. So if we've got this in mass to start with, we can jump straight to, because that is that. But in 10.2c, we don't have that. We have atomic mass units, and remember the first step is to convert those to kilograms, and once we have the kilograms, we're straight to delta E equals mc squared. Okay, so there's your answer to the question at the top in that pink balloon, a pink cloud. 10.2c's got an extra step because you've got to convert the mass from atomic mass units to kilos first. And there's your answer. Work out the change in mass, atomic mass units times what they are in kilograms. And then that number went straight into E equals mc squared, gave us 1.48 by 10 to the negative 11 joules. In our other example, the number that we had for the mass goes straight into E equals mc squared, 2.2 by 10 to the negative 11 joules. Fairly straightforward. This sort of question here is just a revision of what we did back in Unit 1, so I don't want to spend too long on this. This was one about fusion of uranium-235, and it's undergoing neutron bombardment because we're adding a neutron into it. We're getting strontium, xenon, and 3 neutrons come out, so it tends to become a cascade chain reaction that keeps going because each of these can interact with another uranium atom, and it keeps going, getting bigger and bigger, releasing more and more energy. So this is stuff from Unit 1. You've got your masses in atomic mass units. Work out your mass defect. So that is the mass of what you started with minus the mass of what you ended up with. And that mass defect is this energy that comes out. And then we worked out, put that into E equals mc squared. And there's the answers there. I encourage you to pause the video, have a look at those. We've got mass of reactants, mass of products, calculate the mass defect by subtracting them, which is that there. Once we have that in atomic mass units, we've got to put that into kilograms. That's our mass defect in kilograms. That number there goes straight into E equals mc squared. That should be revision for you, although it's been a while. That's why I encourage you to pause the video and read through that carefully. Okay, let's look at an example here. Universal speed limits, where we're sort of coming from. If a 100 kilogram satellite has a force of 10,000 newtons acting on it, so there's a force acting on it, it's going to accelerate. How do we know it's going to accelerate? Because we know there is a mass and acceleration, a force, there's a mass and a force acting on it, so there will be an acceleration as a result. So the question is, how long will it take to reach the speed of light? Now, there's two formulas we need to work this out. That's one of them. And our acceleration formula. Because the acceleration from this will give us that. We know that v is the final velocity, which will be the speed of light. U is its initial velocity, which will be 0. T we want to find out. And what is all this going to start telling us? It's sort of as this table at the side here starts to give us a bit of an idea of what's going on. Down the bottom here we've got the velocity in c, and the blue line is the relativistic momentum versus velocity, and the red line is Newtonian. And it's about half the speed of light that these things start to diverge. And it diverges because of that Lorentz factor. What it means is that the faster and faster you get, the more your momentum is increasing, which means the more energy you need to put in to keep accelerating that mass and get it going faster and faster. It means the closer you approach to the speed of light, the more energy you've got to put in to keep moving that object faster and faster and faster. And that's why we sort of say that the universal speed limit that our equations give us is the speed of light, because at that point your Lorentz factor becomes meaningless and you end up dividing by 0, and that doesn't really work. So let's keep going. You know, a satellite example, force is mass times acceleration, so the acceleration is 100 meters per second squared. How did I get that? Because the force was 10,000, the mass is 100 kilos, find A, which is that. That plugs into our acceleration equation, and that tells us that it would take 3 by 10 to the 6 seconds, because we're dealing with standard units, and my time in this one is in seconds. So it'll take 3 by 10 to the 6 seconds, which is about 1 month. So the question comes, if we continue to apply that force for 2 months, would it go twice the speed of light? The answer there is basically no, it won't, because we reach a point where we start to get to this part of the curve on our velocity versus momentum equation, where the momentum is building so much, it's like it's building up our mass to become bigger and bigger and bigger. And the faster we go, we end up creating more mass because of that that momentum equation we spoke about earlier. And what ends up happening is you need more and more energy to accelerate more and more mass. Hence, you need more and more fuel to do that, and that's impossible to do. You can't ever get that far. So what's likely to happen here is it won't really get to that point in 1 month, because we start to reach this part of the curve where it gets harder and harder to accelerate, and that 10,000 Newton force just isn't pushing as much as it used to. All right, let's start to wrap this up. You've got some nice little websites to have a look at there. I do encourage you to look at the national nuclear body that Australia has, the only nuclear reactor that Australia has. We did look at rest mass and relativistic momentum. We had an equation for that. We came back to E equals mc squared, and we did talk about how the faster you travel, the more your momentum increases and the more energy you need to put in. Hence, you can't keep putting in greater and greater amounts of energy, so you can't ever actually get to the speed of light. We definitely did this one, so we should be right. And don't be like Marty McFly and be a slacker, like the principal tells him in Back to the Future. I hope your principal doesn't do that to you, by the way. Anyway, we've finished this section. We've had a look at all our formulas. You see they've all got ticks next to them there. Okay, don't be like Biff Tannen and get the joke wrong. So make like a tree and leave. I'll catch you next time. See ya.